Okay, if you say so, I will talk about that. Okay. So you will have to bear with my French accent after the beautiful Australian accent. It's okay. Wait, yes. All I'm going to talk about is joint work, is actually the work of my student, Julien Boulanger. With some help from the co-advisor Erwan Lano. And some in collaboration with Irene Paschinelli. And I'm going to consider closed orientable surfaces. With a metric which I assume to be Riemannian with possibly conical singularities. And I'm going to look at the following quantity, which so it's the volume times the supremum over all pairs alpha beta of alpha and beta are closed curves on the surface M. And I take the algebraic intersection of alpha and beta divided by the product of their lengths evaluated with respect to the metric G. Algebraic intersection means, so this is alpha, this is beta, and I count +1 when beta crosses alpha from right to left and -1 otherwise. So this thing, some people call it interaction strength. I have no idea, and I have yet to find a better notation than this, so I'm open to suggestions. I think a good name would be Bill, just for Thurstone. This is the answer to the question, how much intersection can you get per square meter of length? In general, the answer is this. So this guy is bigger than 1 with equality if and only if M is a flat torus. Maybe you should keep in mind the analogy with the systole. So in the case of the systole, you would be taking the supremum over all curves, not pairs, of the volume divided by the square of the length. So it has some analogies with the systole. No, it's not obviously finite. one way, maybe a bit pedantic to say it's finite, is it is the norm of this is the bilinear form on the homology, which has finite dimension, and it's the norm of this bilinear form. So it's norm of a bilinear form over a finite dimensional space, so it's finite. No, you whatever you want. Yeah, but actually, anyway, I'm beyond this. Some obvious questions are, for instance, let us look what is true in higher genus. I have no idea. We could specialize the question to, for instance, hyperbolic metrics without singularities. I have no idea either. For instance, I do not know whether the Bolzan surface, yes, in the case of the systole is a mean, so it is interesting to make it big. Here, I'm taking a soup, so it's obvious that it's easy to make this go to infinity by pinching some curve. If the length of alpha goes to 0, this is going to infinity. So it's not hard to make this big. What is hard is to make it small. The interesting surfaces should be the ones for which this guy is small. And I have no idea whether the Bolzan surface minimizes it in genus 2, even among hyperbolic surfaces. Yes, in general, it's a supremum. There exist surfaces for which it is a maximum, but there are also plenty of surfaces for which it is a supremum. So, since I don't know anything, I'm going to start low, and I'm going to look for surfaces which have higher genus, but look like a flat tori, and that's translation surfaces. So I'm going to start a long digression about translation surfaces. And which surfaces. So what is a translation surface? It's very simple. You take a polygon in the plane. So this is a polygon. And you want this polygon to have its sides, pairwise parallel with the same length. So I think it should be okay. This is parallel and with the same length as this, and this with this. So I identify pairs of sides with the same length and the same direction. And I get a surface, and that's called the translation surface. It's called a translation surface because since you identify parallel sides, you have a well-defined notion of direction on a translation surface. And a nice thing about translation surfaces is that they come with a GL2R action. Because I have this polygon in the plane, I can act on it by some matrix, and the new polygon will still have its sides, parallel and with the same length. Yeah. Yes, exactly. Yeah, but I thought that was. Yeah. Here, I'm not interested in dilations because for me it's going to be the same surface. So actually, I'm only going to consider SL2. And an example of an action is you take everybody's favorite translation surface. You take, and this gives you this. To answer Norbert's question, if you take T irrational, that's an example of a surface where K-vol is a supremum and not a maximum. And when you act by a matrix, the polygon always changes if the matrix is not identity, but it may happen that the surface that you get when gluing the sides is the same. Example, you take the square and you act by this. You get this, but this is the same as a surface. This is the same as this because okay, you cut here, you glue this triangle again here, and you get again the square if your drawing is done correctly, which I cannot do. And when this happens, we say the matrix lies in the Vich group of the surface. So this is the matrix M, and this is the translation surface X. Translation surfaces are always called X. And in this case, I say that M lies in the Vich group gamma of X. So it's a group of affine symmetries of the translation surface. And obviously, if you take as your translation surface the square of the torus, the Vich group is SL2Z. In general, you may have all kinds of groups, but these groups are always discrete and never co-compact. So the best you can hope, in a sense, is that your Vich group has finite covolume. And in that case, we say that the surface is a Vich surface. There are lots of examples of Vich surfaces. Obviously, the torus is one. Here is another one, which is less obvious. You take a regular pentagon, you take two copies of it. And now you observe that this has sides pairwise parallel with the same length. You glue them. You get a surface of genus 2. I leave you compute the Euler characteristic. This is a translation surface, and actually it is a Vich surface, and its Vich group is almost a triangle group. So if X is this, then the Vich group is generated by I'm going to cheat. Vich group is generated by the rotation by pi over 2 and a translation by this. Okay, this is false because you are going to tell me I don't see any rotation by pi over 2 is this, but I'm going to come back to this. So who are the Witch surfaces? So here is an almost complete list. So you have the regular polygons. Because of course I could also have taken here a regular octagon, and identified its sides in pairs, and I would also get a Witch surface. You have a mysterious family called the Boole-Moller surfaces. You have infinite families in genera 2, 3, and 4. Which I'm not going to describe because of course, when you have a Witch surface, you could take ramified covers. For instance, if you take a ramified cover of the square torus, you get what is called a square-tiled surface. So you can always do that, and you again get a Witch surface. Then you have some sporadic examples, and that's all. At least it's a conjecture. But if it's a conjecture, it's not very far from being a theorem, because I think the only remaining open case is when the genus is 5. So this is true, maybe except in genus 5. Oh, yes, it's countable. Yes. Sorry. No, it's not a, oh yeah, I should have drawn fundamental domains. Oh, they are not translations, they are elements of SL2. For instance, if you take the square torus, the Witch group is SL2Z. Does that answer your question? Oh, well, in this case it's easy. Yes, I'm not going to speak about those guys because precisely they have complicated fundamental domains, and I don't. And all we do relies on the geometry of the fundamental domain. But I'm going to be interested in those cases because the Witch groups are triangle groups, or maybe at least they are commensurable to triangle groups. For instance, for the double odd sides gone it's generated by this. And here you replace the golden ratio by 2 cos of pi over n, where n is this. You have, it's almost the same for the even side gone, and the Boole-Muller surfaces. So the Boole-Muller surfaces is an infinite family with 2 integer parameters. So I'm going to call them x, n, m. And in this case, the triangle group, it comes from the triangle 2 to n plus 1 infinity. So this, does this answer your question about the fundamental domain? Okay. For the triangle, you have this. And the Boole-Muller surfaces correspond to the triangle n, m, and infinity. I'm going to draw a Boole-Muller surface just for the heck of it. Yes, excuse me. Yes, absolutely. Yes, you are right. They are discrete as Fuchsian groups, and they have finite covolume as Fuchsian groups. Excuse me, say again. Which surfaces you mean? Only countably, which surfaces you mean? Yeah, no, it's definitely not easy. No. At least not right now, but. So I'm going to draw a Boole-Muller surface just to give you an idea what it can be. So here is a Boole-Muller surface is made of n polygons, and the polygons are regular m-gons, except for the extreme ones. So here is so this surface has 4 polygons, 2 of which are regular hexagons, and 2 of which are equilateral triangles. And now I'm running out of space. So this is and this one looks like this. So this one has 3 polygons, 2 of which are squares, and 1 of which is a regular octagon. They look like this. And I leave it to you to check that indeed. And you have to, the rule is that you identify a sides of one polygon only with the next or with the previous one. And I leave it to you to check that there's only one way to do that and it works. It's not obvious at all that this has a this group, which is this, but okay. Yes. Now I need to speak about the Teichmuller curve of each surface. Of any translation surface, actually. Is just the quotient of the hyperbolic plane by the Witt group. So which surfaces are the surfaces for which the Teichmüller curve is has finite volume. So I call this Teichmüller curve, and the Teichmüller disk is the lift of this in the Teichmüller space. So you can view this as a subset of the moduli space of complex structures on the corresponding genus, and you can lift it to the Teichmüller space, and then you get a Teichmüller disk. Excuse me? Yes, exactly. For each surface, you have one Teichmüller curve. Does that answer your question? Yes. Okay. Yes, but does that your question seems to be independent? This is a curve in the moduli space. So X is you can view X as a point in this, and yes. Yes, well, then when X is a flat torus, gamma of X is SL2Z, and so this is the usual thing like this. Does that answer the question? Yes. Yeah. So in all the examples I'm going to look at, since this group is a triangle group, or almost, the Teichmüller curve is going to look like this, with one cusp and some special points with lots of symmetries. Okay. And now I think I can almost state my result, not my results, but the results. Yes. Now, this was a crash course on Vich surfaces. Now I'm going to come back to computing my guy K-vol. So why is it interesting to compute K-vol on translation surfaces? You remember that we had this this expression here. Note that on a translation surface, any closed curve can be developed to the plane. So I'm going to identify alpha and beta with their do you call that holonomy vector maybe? Okay. I just take a curve and I develop it to the plane. So that means that the expression alpha wedge beta is well defined. But alpha wedge beta, that's the product of length times the sine of the angle. And observe that this quantity has the good taste to be invariant by SL2. So it's not going to vary over the Teichmüller curve. And the algebraic intersection is topological, so obviously it doesn't change when you apply a matrix to your surface. So in this expression, the only thing that varies over a Teichmüller disk is the sign of the angle. So that makes it a bit easier to compute K-vol over some special Teichmüller disks. And that's what we do. First, I'm going to give a geometric interpretation of sine of theta in terms of the Teichmüller curve. Maybe in the special example of the flat torus. So what, maybe it's a well-known fact, choose your favorite homotopy classes on a flat torus. Do you know what are the flat tori in the moduli space of flat tori for which these two homotopy classes of geodesics are orthogonal? Yes, exactly. Yes. Yeah. So I'm going to rewrite what Norbert just said. So I'm saying that so I have my translation surface X. I'm going to consider the set of translation surfaces X prime in the Teichmüller curve, which I'm going to like this. No. So I'm considering the set, I'm choosing two homotopy classes of closed curves in the surface X. And I'm considering the surfaces which are obtained from X by a matrix of in SL2, such that in this new surface, my curves alpha and beta become orthogonal. And I'm saying that, as Norbert said, this is the geodesic in H2 with endpoints, the coslopes of alpha and beta. Example, you take the flat torus, and you take as your homotopy classes alpha and beta, you take the sides of the square, so you take this as X, you take this as alpha, this as beta. You have the fundamental domain for the Vich group, which is this. Alpha is horizontal, so its coslope is infinity. So it's up there. And beta is vertical, so its coslope is 0, so it's there. So the corresponding geodesic is this, which corresponds to the matrices, I'm going to call it G. So G corresponds to the matrices like this. And you agree with me that when I act by this matrix on this, the curves alpha and beta remain orthogonal. And since Norbert has already won the prize, do you know, now I ask which are the surfaces in which alpha and beta make a given angle, say theta? Okay, so the answer is, I need colors. The answer is something like this. So that's the boundary of a tubular neighborhood of the geodesic, which is here, such that at the endpoint they make an angle theta. So the yellow curve is the set of x prime in the Teichmüller disk, such that the angle between alpha and beta is theta. And now that gives an idea to compute k-vol over the Teichmüller curve or disk. Yeah, it's more convenient to lift everything to the Teichmüller space, so I'm going to speak about Teichmüller disk from now on. So what do assume you are a surface, and so you have a Teichmüller disk, you have a fundamental domain for your Vx group, and you are a surface, say you live here. You are x prime rather. Usually I put x here. And so what do? You are going to look at all pairs of curves. So what are pairs of curves? Pairs of curves are just geodesics with some special endpoints. And for each of those geodesics, so if you consider those geodesics as dealers, they have something to offer you. For each geodesic gives you some value of intersection, length, and length. It does not matter, but if they are not simple, they are never going to realize the supremum here. So they are simple closed geodesics by construction. Because if you self-intersect, then you are homologous to something that is shorter and does not self-intersect. Does that make sense? So I am living here. I want to compute my k-vol. So I have to look at lots of all possible pairs of curves and see which one gives me the best deal. But then I have to consider that I have to pay for transportation. So transportation is measured by the distance theta. Yes, by the way, you have, I'm sure Norbert knows that, the distance between this point and this geodesic is 1 over hyperbolic cosine of sine of theta, something like this. And so this theta, it's some kind of transportation cost. You have this value here, but you have to take it to your surface. So what I'm doing is I'm taking all possible pairs of geodesics. Each of them gives me some special value, and then I factor in the transportation cost, and I choose the best deal. And now I think I can state the theorem that needs a new blackboard. So the idea is you should look at the alphas and betas, which are going to give you the highest value of intersection over product of lengths. And then you have to consider how far can you get from the corresponding geodesic in the Teichmüller curve. So the first result is joint work between Julien and his advisors. And it says the following. It says that on the double outgone, the best dealer is always this geodesic. Wherever you are in the fundamental domain of the V group, your best option is to buy from this guy. This guy corresponds to pairs of sides of the doubled, the 2n+1 gone. So the result is for any surface in the Teichmüller disk of we have bill of x is some constant which I'm going to write. So what I called sign of x and 0 and infinity is, this is the geodesic 0 infinity, this is x, and this is theta of x 0 infinity. And k0 is, I believe it's n/2 times cotangent of n/2, something like this. So in that case, the result is very simple to state. So there is a second theorem by Julien himself. It says the following. So that's for the regular 4m gone. And that's where the situation gets hairier. So in the case of the 4m gone, the fundamental domain looks like this. It has two cusps. And in this case, you have many good dealers. So the 4m gone is sitting here. You have this geodesic, which corresponds to pairs of sides of the 4m gone, and you have infinitely many other ones which accumulate on this one. And so in that case, the result is for each surface, you look, for instance, imagine you are sitting here, so you look which of those two guys is closest to you, and then you buy from this dealer. So and then I have to write so I'm calling G this set of geodesics. And the last theorem is about Boole-Moller surfaces. So that's by Julien and Irene Paschinelli. And in that case, the result is as simple to state as in the case of the 2m+1 gone. The circular disk looks like this. The surfaces S, X, Mn, and X, N, M. Yes, I'm assuming that N and M are mutually prime. The surfaces XNM and XMN lie in the same triangular disk. So I put one here and one here. And there are exactly two good dealers, which are those guys. And so the result is the same. If you are sitting here, for instance, you are going to buy from this dealer. And if you are sitting here, you are going to buy from this one. And you have something like this. You have some constant, which corresponds to the value on those geodesics, time 1 over the hyperbolic cosine of the distance between X and this guy. How much time do I have? Chairman, do your office. Okay. Well, okay. So I just say a word about proofs. So how do you prove that? So what the solution that Julien found was to so first, he starts by computing k-vol in the particular case of the surface with most symmetries. For instance, in the case of the double pentagon, what he does, he takes a curve first. You can always assume one of the curves is horizontal by acting by the Veitch group. So assume one of the curves is this, for instance. Then you have your beta, which is like this. And then the idea is to cut beta into pieces which intersect at most once with alpha. So the obvious thing is to cut each time you cross a boundary, you cut. And so two such pieces cannot intersect several times, and their length is at least the length of a side, except in the bad case, and the bad case is when you have this. So those guys can be arbitrarily short. So in this case, you have to take into account the continuation. Two such guys cannot intersect more than once, except maybe something like this happens. So there is an infinite quantity of small difficulties, and you have to take care of them at the same time. So it's like there is a million mosquitoes trying to bite you, and you have to fight all of them and without getting mad. And so it takes a very organized person, and that's why Julien was able to do it and not me. And I stop here. Thank you for your attention.